Hello friends, in this video we are going to discuss about Cauchy's integral formula for derivative of an analytic function. This is lecture number 15. Okay, this is lecture number 15 of complex analysis. So here you see, let me tell you one thing, that we have already discussed about Cauchy's integral formula in the last lecture, in the previous lecture. So you must know that Cauchy's integral formula in order to understand this Cauchy's integral formula for derivative of an analytic function. So two different things that we have already discussed. One, Cauchy's integral formula in the previous lecture. Okay, now we are going to discuss about Cauchy's integral formula for derivative of an analytic function. Okay, so first of all I would like to suggest that you watch the lecture number 14. Okay, I have given all the links from lecture number 1 to 14 in the description box. You may go through if you want. Okay, if you watch from the lecture number 1 to this, then you will understand better. Okay, what is complex analysis and all the related things that you must know, you must be aware of those things. Okay, so now let me tell you one more thing. When the next part will be uploaded, that gonna appear at the end of this video. Okay, so and you can check the playlist for different other courses as well, for Laplace transformation and differential equation, etc, etc. So there are many courses in the playlist. Okay, so before we start, please subscribe the channel if you are new to my channel. Hit the bell icon and hit the thumbs up button if you like my videos, and share with your friends. Inspire me to create new videos, new contents for you, help me to grow my channel. Okay, and don't forget to hit the bell icon. Okay, that's important. So now let's start. So Cauchy's integral theorem formula for derivative of an analytic function. Okay, so this theorem says that you can see this formula is this: if a function f of z is analytic in the region R, then its derivative at a point z is equal to a. Then its derivative at any point z is equal to a of the region R. At any point, then its derivative at any point z is equal to a of R is also analytic. Okay, in R. That means if the function f of z is analytic in the region R, then derivative of the function f of z at any point z is equal to a, which is also analytic at the region R, and that is given by this formula. Derivative of f of z at z is equal to a, that is f dash a, is 1 by 2 pi I integration along c. I'm gonna let you know what is c here. F of z divided by z minus f whole square dz. So here c is the curve, any closed curve in the region R surrounding the point z is equal to a. Any closed curve in the region R surrounding the point z is equal to a. So in the region R, so this C is a curve that surrounds the point z is equal to a. That's it. So now you see the derivative at the point z is equal to a, derivative of this function f of z at z is equal to a is given by this formula. So let us prove this. Okay, so now let me go to a new slide. In order to prove this theorem, first we're going to use this Cauchy's integral formula here. So we know the Cauchy's integral formula. Cauchy's integral formula is this: f of a is equal to 1 by 2 pi I integration along C f of z divided by z minus a dz. So we have already discussed about this formula in the last lecture. Just go through the lecture number 14, link in the description box. Right, now let us differentiate this equation. Let it be equation number 1, and differentiating equation number 1 with respect to a. What we're going to have, if you differentiate with respect to a, then this is going to be f dash a, then 1 by 2 pi I integration along C. Then here we're going to have f of z, as we are differentiating partially with respect to a, so that's why f of z should be taken out of the differential coefficient, and we're going to differentiate 1 by z minus a, right, dz. Okay, so if you differentiate this, then what you're going to have, see, if you differentiate this, you can differentiate it this way, del a of 1 by z minus a. So it can be assumed this one, del a, partial derivative with respect to a, 1 by z minus a means z minus a whole to the power minus 1. If you differentiate it, it's going to be minus 1 z minus a minus 2 into, then again you have to differentiate the terms within the bracket, that is z minus a. If you differentiate z, that's going to be 0. If you differentiate minus a, that's going to be minus 1. So this minus, and from here you're going to have minus, so that's going to be plus 1. So plus z minus a whole to the power minus 2, that's what you're going to have, and that is nothing but 1 by z minus a whole square. That's what we're going to have, right? So that's why we're going to have this f dash of a going to be equal to 1 by 2 pi I minus c here, f of z, here it will be z minus a whole square dz. That's what we're going to have, right? Now you see, this is what we needed to prove. Okay, so here if you go back to the previous slide, so this is the formula that we needed to prove, right? So hence it is proved. This is proved. Now from here we can find second order derivative also, third order also, and nth order also, because this is very important. So that's why let me show you that one as well. So now let me copy these things and let me go to the next slide. Okay, so here you see, if you differentiate this again, just let me clear these things. So if you differentiate it again, what are we going to have? If you differentiate it again, 1 by 2 pi I integration along C f of z del a of 1 by z minus a whole square dz. If you differentiate this, that what it's going to be? It's going to be minus 2 into z minus a, and then again differentiation derivative of z minus a, that's going to be minus 1. So it's going to give you here it should be power 3, minus 3, minus 2 and minus 1, minus 3, right? So here minus 1 into minus 2, that's going to be plus 2 by z minus a whole cube. That's what we're going to have, right? So what we have got here, we're going to have 2 by 2 pi I integration C f dash z divided by z minus a whole cube dz. Okay, so similarly you can find third order derivative of fz at z is equal to a. Then what you're going to have? Then you're going to have 2 into 3 2 pi I f of z, it should be f of z, z minus a whole to the power 4 dz. That's what we're going to have, right? So this 2 can be written as factorial 2, and 2 into 3 can be written as factorial 3, right? So you can write this one as factorial 2, and 2 into 3 is 6. 6 is nothing but factorial 3. This is factorial 3. Similarly, if you find nth order derivative, so when there is power 4, this is factorial 3, this is third order derivative. So when there is n, here you see this is nth order derivative at z is equal to a, then that should be n factorial here, 2 pi into I integration c f z z minus a. So if this is a nth order derivative, then the power should be n plus 1, right, dz, because when there is third order derivative, here you can see the power is 4 here. When there is second order derivative, then power is 3 here, right? So this is also a very important result, so we must remember this. So in the next video, we're going to solve problems using Cauchy's integral formula, Cauchy's integral formula for derivative of an analytic function as well. So, and those problems will be taken from the H.K. Das book, mathematical physics books by H.K. Das. Okay, so see you in the next video. Thank you for watching. Bye bye.